This will be just as an extension of what we were working with before with the kinematic equations. We're going to start with a couple of conceptual questions, and then we're going to move to just another practice problem. So here we go with 4a. Can an object be accelerated? And let me emphasize that. Can it be accelerated while traveling at a constant speed? And so in this case, we need to look at what constant speed implies. In this case, all we were talking about is the magnitude. It is just a scalar quantity, so we don't need to worry about the direction. In this case, the acceleration can just be a change in direction, which means that we could still be at a constant speed and we could be accelerated. The example here would be is if you are going around a corner and your speed remains the same, but your direction changes. Because your direction changes, you have an acceleration. Now for part B, can an object be accelerated while traveling at a constant velocity? In this case, velocity has a magnitude and a direction, and any acceleration will change the velocity. So if we use the same example of going around a corner, our velocity is changing as we go around the corner, even if we're going at the same speed, because our direction is changing. If our direction is changing, that means that we must have an acceleration. Light travels in a straight line at a constant speed of 3 times 10 to the 8th meters per second. What is its acceleration? In this case, we are told the magnitude and the direction, and that it is constant the entire way. So in this case, if light travels in a straight line at this constant speed, its acceleration is 0. It doesn't have an acceleration. So in this case, if you're told about both the magnitude and the direction, and that both are constant, your acceleration must be 0. Now number 6. It takes a car 6.4 seconds to stop after the driver starts braking at a velocity of 32 meters per second. The deceleration is at a rate of 5.0 meters per second squared. How far will the car travel before it stops? So let's go and start listing out our variables here. We are told the time, so we can say our time is 6.4 seconds. Starts braking at a velocity of 32 meters per second. And so in this case, this is our initial velocity, so our v naught is equal to 32 meters per second. The deceleration is at a rate of 5.0 meters per second squared. In this case, here is the magnitude, and the direction we're told is the deceleration. So if we're told something like this, that means that our acceleration is negative. So negative 5.0 meters per second squared. How far will the car travel before it stops? So that tells us that we are looking for our d, and the term stops tells us that our final velocity is 0. So when we look at this, we see we have our time, we have our initial velocity, we have our acceleration, we're looking for our distance or displacement, and we have our final velocity. We have all of our variables, so this means that we can use any equation that has displacement. The easiest one in my mind to use is d is equal to 1/2 times vf plus v naught times time. What you'll notice here is we are actually ignoring the acceleration in this case. You could easily use the acceleration in one of the other equations, and you should get the exact same answer. In fact, for a problem like this, being able to work out the problem twice using 2 different equations is a great way to check your work. So in this case, we have d is equal to 1/2 times vf, which is 0, plus 32, which is our initial velocity, times our time, 6.4. When you work this out, we get D is equal to 102.4 meters, which is what your calculator will give you. We look back at our problem, and we have 2 significant digits in each of these. And so in this case, only these first 2 digits can be significant. Because of the way this value is, we will have to use scientific notation. So D is equal to 1.0 times 10 to the second meters. And there we go.